Everybody, greetings. Welcome to the Hariri Institute for Computing at Boston University. I'm Stephen Brown. I'm the Director of Finance Administration at Hariri, and I'll be providing an introduction to today's program. First, a little bit about the Hariri Institute. The Hariri Institute for Computing at Boston University is dedicated to leading integrated initiatives in research and technology development, while targeting a broad set of disciplines at the nexus of computational and data sciences. With core strengths in cloud computing, security and data privacy, and artificial intelligence, as well as a network of over 300 plus research affiliates across a vast spectrum of disciplines, the Hariri Institute is positively impacting people both inside and outside the Boston University community. A little bit about today. This is the program for today. The first 5 minutes will be me introducing our host, as well as another 5 minutes after that for an icebreaker. The bulk of our talk afterwards will be 20 minutes of our featured speaker and half an hour afterwards for a Q&A session. If you have any questions at any time for our featured presenter, please enter them in the chat feature of Zoom. Today's seminar is a part of the Did You Know You Could series. The Did You Know You Could series provides a venue for people to learn skills that are either enable or are enabled by computing and data science. Topics they might not even realize they need to know. They can also meet other similarly inquisitive people while adding more tools to their belt. The series is intended to be an informal, low barrier mechanism for convergence and skill building, and welcomes a broad audience of students, faculty, and staff from across the landscape of disciplines at Boston University. The series itself is led and organized by our graduate student fellows. In addition to today's talk, we also have a talk on neural networks on February 28th from Mark Howard, another talk on March 3rd on the effect of car ownership on electoral participation from Maxwell Palmer, and another talk on March 24th, on brain-computer interfaces and restoring speech with Frank Gunther. Finally, to introduce today's host, Hasini Weerathunge. Hasini is a PhD student at the PhD student in biomedical engineering at Boston University. Her research interests include brain-computer interfaces and neuroengineering applications that enhance the human quality of life. As a graduate student in Dr. Kara Stepp's Sensory Motor Rehabilitation Engineering Lab, her research focuses on utilizing auditory and somatosensory motor perturbations of voice and speech to develop neurocomputational models of speech motor control for motor speech disorders. Hasini received her BS in engineering from the University of Weerathunge in Sri Lanka, where she majored in electronic telecommunication engineering. Her undergraduate research was focused on objective hearing, screening of newborns via automated auditory brainstem responses.
Thank you very much, Stephen. It's my great pleasure to host and introduce our featured speaker for today. Before we get started, I want to remind folks to follow the Hariri Institute channels to get the latest updates on upcoming events. And today's event, I also want to remind you that it's being recorded and will later be on the Hariri Institute's YouTube channel. Okay, so I'd also like to take this opportunity to get to know the audience in today's Did You Know You Could series a bit better, and to understand what each of you hope to learn from today's presentation. So please use the Zoom chat option to provide us some insights. So my first question for today for you is going to be, what is your field of study? So if you can just type in the chat your field of study, we can get an idea of who's in the audience and what you're hoping to get out of today's presentation. Right. Okay, so we have people from astronomy, speech, language, and hearing sciences, space weather, mechanical engineering, machine learning, a lot from speech, language, and hearing sciences. Yes, so so there's a lot of different fields interested in this very generic topic of statistics. So my next question is going to be a poll question. So I'll open up the poll right now. The question is going to be, what degree of familiarity you have with today's topic. Are you a statistical guru? Do you know a lot about statistics or little to no knowledge? So I'm going to give 1 to 2 minutes, 1 minute essentially for you to answer the poll. Right. So let's give another 30 seconds. All right, I think we can pull up the poll answers right now. Yes, so there's a fair divide between the amount of knowledge that our audience have today. But a fair few have a little, or they're fairly familiar with the topic. So that's good. So my final question for the icebreaker round is going to be, what do you hope to gain from today's presentation? Just put 1 sentence or phrase today. What are you hoping to gain from today's presentation in the chat? All right, so maybe you can put that, like think about it throughout the presentation today too. Yes, demystify how to approach statistics. Yes, thank you, Kim. So without further ado, I'm going to go ahead and introduce today's speaker. So our speaker for today is Eric Kolacyzk. He currently serves as the director of the Hariri Institute for Computing, and he's also a professor of math and statistics at Boston University. He was named a data science faculty fellow at Boston University in 2018. His current research interests involve mainly around the statistical analysis of network index data, with a particular focus on both foundational issues and statistical problems arising in practice. His applied work in network analysis has included collaborations with researchers in areas like bioinformatics, computational neuroscience, computer network traffic analysis, and also social work. Eric's previous research was concerned with the development of statistical multi-scale models with applications in areas including astronomy, computer science, geography, and remote sensing. So I'm going to give over the screen to Eric in a bit to share his slides and start the presentation. In terms of Zoom logistics, I'd like to remind the audience to use Zoom chat window to ask any questions during the 20-minute presentation. We'll have a 20 or 30-minute question and answer section at the end of the lightning talk to explore questions in more detail. So Eric, without further ado, over to you.
Okay, thank you, Hasini. Let me share my screen here. Hang on. Let me now try and share my screen. Okay, can you see that? Is that full screen?
Yes. Yes.
Yes, okay. All right. So yeah, thank you for the introduction. It's interesting experience to speak in in my own seminar series that we developed here at the Institute. I have to admit, you know, we've been very keen on trying to get people to stick with "Did you know you could" for their titles, and I broke that rule. But I thought that it would be more useful to break it this way. So I'm going to talk about something that you know, I've been passionate about for a long time. I have a traditional statistics PhD, although I spent many years in systems engineering and related areas. As Hasini read, I've had the pleasure of collaborating with people in lots of different domains. My thinking has gradually moved from the sort of focus I had initially as a PhD student earlier, where it was very much in terms of the methods I was learning and their application and the software to do them, and gradually zoomed out and out and out. This perspective has now gone into my classroom. It's gone into publications I've given, talks I've given. You'll see I have a shout out to an NSF committee I was on, where we ended up pulling that into a theme into the report. So it's really very much sort of gone through everything that I do. And I wanted to share it with you. What I'm not going to be sharing is I'm not going to necessarily be sharing with you a specific technique or a specific way to make Python calculate a certain number or something like that. Rather, I'm going to share with you sort of the essence of how I approach statistical problems. And I hope it's useful to you. It's actually how it's at the core of how we teach our MS in Statistical Practice program, or the MSSP program here at BU. So I do think it's a perspective that really helps and works. So let's start with kind of where I think many of us begin with, right? So this is sort of meant to be illustrative. Most people that I encounter seem to associate statistics with output, right? So if you say, I've done some statistics, can I show it to you? I almost always know I'm going to be looking at computer output. I'm not going to necessarily be looking at sort of an idea sketch or goals or things like that. It's almost always going to be output. And, whether or not this is part of an analysis, whether it's sort of one piece of a larger data science workflow, or it's part of an AI system, this really is just the tip of the iceberg for actually doing statistics, right? And so in that spirit, I thought I'd make an iceberg plot for you to kind of capture what I feel is what we're looking at. So these iceberg plots, if you haven't seen them before, right, the idea that, you have the tip of the iceberg outside of the water and all the rest of the iceberg is under the water, but no one sees it, right? So what people think doing statistics is largely, I think, often the statistical output or the handful of commands or whatnot that one does to produce that output. But really, there's a vast amount of words I could put here underneath. It's just a handful of them, right? I mean, certainly data provenance is key. Thinking about where the data came from, how you got them, is it designed, is it observational, what sort of data cleaning you did. The methodologies that people are using, machine learning is certainly a big one now that we use in a lot of statistical analyses, the computing that underlies all of this work, a balance of theory and practice, which I'm going to return to later. And then, of course, also collaboration and communication, right? All of those are really what doing statistics is. But as I said, we often just see the output at the end, right? So why the confusion? I think a lot of it is on those of us who teach statistics. I think what we've arrived at is sort of a forest from the trees situation, right? So as you can see in the cartoon there, right, there's being cautioned that the trees obscure the view of the forest. I think that the very way that we often go through our Stat 101 courses in particular, where there's just so much that for a variety of complicated reasons is squeezed into one course. That it is very much, here's how you do it, here's how you do it, here's how you do it. Here's a problem, here's how you do it, this is the answer, copy it. Yes, no, you got it right, boom, next one, right? So this is not just statistics. It's also, I think, in a number of areas like mathematics, physics, programming increasingly these days. I think the STEM fields are challenged to try and both communicate successfully what needs to be done, but then also somehow pull out of that enough to be able to communicate the forest as well, right? And I know there's lots and lots of really excellent efforts out there across these different disciplines working at it, but it takes a long time for pedagogical change to work its way into disciplines. So in the meantime, what can we do? Well, this is my perspective on learning, and I've had it on my website for over 20 years. I've had it on various websites since I've changed websites over 20 years. It's taken from an ancient Chinese text of Chuang-Tzu. So this says, the fish trap exists because of the fish. Once you've forgotten the fish, you can forget the trap. Right? And the rabbit snare exists because of the rabbit. Once you've gotten the rabbit, you can forget the snare, right? Words exist because of meaning. And once you've gotten the meaning, you can forget the words, right? And then he's sort of cute in the end and says, where can I find a man who's forgotten words so I can have a word with him, right? So I like that quote partly just because the end is a really nice closer, I thought. But the essence of it, I think, really captures what we're trying to do when we're teaching a lot of these STEM areas like statistics, right? We have all these drills and small exercises and whatnot, but we're really not looking for you, despite appearances, to be able to reproduce a t-test exactly or reproduce an ANOVA table or whatnot. We want you to do that, but then we want you to forget about that, right? And we want you to be able to back out and understand what you're attempting to do with that t-test as a tool, with those histograms, with those visualizations or whatnot, right? And that's hard, I've found. So here's another mantra. This is one that I threw out in a class at BU. It's MA 575. It is the upper level course that seniors take and master's students, some PhDs take as well. It's meant to focus on linear regression, but really what's under the hood, right? So people have seen linear regression 3-4 different classes by this time. This has a linear algebra prerequisite, a probability prerequisite, and we really open up the car, not just learning how to drive it. And we try and figure out, why does it work? And they see a lot of theory and they see a lot of practice. And the students in a number of years are trying to figure out how to get my practice and my theory to work, because they were very used to keeping theory in one part of their brain, practice in another, right? And never shall the twain meet. And that's actually not how it's supposed to work. So I threw something up on the board, right? I just said, theory informs principle, principle informs practice. And I had a bunch of these looks in the audience. I thought, that actually sounds pretty good. And then I went to a NSF conference on STEM education, forward-looking. And we sat down and they had a bunch of these cutesy things. I have to say, I don't like these things, right? Where they have a bunch of little pads, they have a bunch of things to play with and a bunch of markers and stuff. And you're supposed to visually create what you're trying to communicate. Now, if it were me, there'd be nothing there except a pad of paper, and I would have written this on a pad. But I shared it with people and someone said, oh yeah, and practice in turn informs theory. And then we ended up together making this little diagram there that you see on the right. Right. And so this made its way into an NSF Crossroads report, for better or for worse. But you can see the theory informing the principles informing the practice, right? And all of this continuing to sort of cycle. Right. So I'm not the first one who's thought about this, certainly. Stephen Stigler is emeritus at University of Chicago now. He was not only an excellent statistician and at one point president of the American Statistical Association, but he also was in their Ideas and Rhetoric and Methods program at Chicago, which is a very broad, cross-cutting area that brings people from the humanities, social science, et cetera. And Steve's particular angle is looking at the history of statistics. Right. And so he wrote a book published by Harvard University Press about a decade ago, and he tried to pull together what he called the 7 pillars of statistical wisdom, right? And these are what he had there if you haven't looked at it. I had to crack my copy open again over the weekend just to remind myself of what I'd looked at a while ago. So he talks about aggregation, information, likelihood, intercomparison, regression, design, and residual, right? And I suspect on the one hand, people feel those look familiar. On the other hand, you may be thinking, that's it, right? That's all there is to statistics. What about your t-tests? What about, your ANOVA tables or whatever? So if you look at his table of contents, that's actually very revealing, right? So under aggregation, he said that's not just sums, but from sums you can get means, right? But it also means tables and least squares. Right. And more essentially, it is the principle of presenting less data rather than more to actually capture what's going on. And if you read the book, he says, historically, that actually was a major innovation, that it was felt that you'd never, ever throw away a data point and you have to communicate all the data points. Now, in the era of big data, if they hadn't figured that out already in our current area, we would by necessity be figuring that out, right? But it was an innovation in its time. Information is talking about measurement and the rate of change. Likelihood is basically talking about calibration on a probability scale. It includes maximum likelihood methods, but really it's talking about calibration. Probabilities are talking about uncertainties, right? And they're a way of calibrating it. Inner comparison is talking about within sample variation as a standard. The number of times that I've talked to people about analyses and they want to know essentially, is this big what I saw, or is it different? And the conversation boils down to compared to what, right? That's the essence of what lies behind ANOVA and all the other related techniques that one has. Regression, you think about least squares, you think about y equals a plus bx, but from that we have everything from multivariate analysis to Bayesian inference to causal inference and machine learning, right? All of that is built on that foundation. It's the same principle, just with key important different elements. Design is experimental planning, the role of randomization, right? Randomization in turn is entered even into things like bootstrapping, right? And then residual, not just the residuals of your regression, but really thinking about the ever evolving process that we do in terms of science and modeling. My model has captured such and such. What is it beyond that that I'm missing? This is actually built into a bunch of recursive learning algorithms in machine learning now, whether you're talking about AdaBoost or you're talking about recursive machine learning or whatnot. He steps back and he summarizes this even bigger picture, right? He talks about the value of targeted reduction, right? The diminishing value of an increased amount of data. That's something that is coming into the essence of deep learning algorithms these days when they talk about batch learning versus mini batch learning and about how to schedule a schedule to go through a near infinite amount of data. The principle of diminishing value is built into that. How to use probability as a measuring stick, including our discussions about p-values these days. What is a p-value? How useful is a p-value? Should we abandon p-values, right? Really, it comes down to, are they useful as a measuring stick for what we're trying to talk about, right? So let me give you a quick example, and then I'm going to just shut down, and we're just going to see where our conversation takes us. Because I can say, as one of the originators of the series, that was an important thing of these series too, was just to see, as if this were a brag bag lunch series, where conversation takes us, right? So here's an example about averages, right? So averages are a form of aggregation. This is some made up data, right? We have responses from a group of people identifying as female and male, and then we have the corresponding averages, right? And this is very familiar, and you might do two sample t-tests, or you might do non-parametric versions or whatnot, but basically it is combining the notion of aggregation and inner comparison. On the other hand, what may be less commonly known is that we are in cutting edge research. My group is doing some of this as well. On the right-hand side, we're talking about how do you average data like that, right? So if I give you 10 networks that are the social neighborhoods of people on Facebook, right? And each of those female and male responses are instead given by female and male networks. Can I average the male networks and average the female networks, and can I compare them? Right, this is important both in social networks, and also it's used routinely now in computational neuroscience. So these ideas are very fundamental, and yet they're still pushing with new data types, unstructured data and structured data in the current big data era. They're still pushing cutting edge research. This is the use of probabilities, right? This is probably familiar to everyone. If you have two types of observations, X's and Y's, you look to see with enough data whether the shape of them looks normal, perhaps on the x-axis, the y-axis. If you've seen a bit more probability in multivariate methods, you may have seen the flat part as well, seeing that you often get these sort of bell-shaped curves that show over the data, right? And then you learn at some point that somehow many things behave this way, right? And a few rules as to why, right? So that's a theory principles thing, right? So this idea of somehow going from these curves and the rubric that somehow a lot of time it happens. How do we know a lot of time it happens, right? Did we somehow aggregate all the experience we've had in the last 200, 300 years? Or is there something more, right? And a lot of that something more is theory, right? And so what I've done here is I've put just a handful of statements, and then I've put formal theorem names. right? So some or all of you may have seen at least some of these theorems, or maybe all of them, right? So here's first statement, right? The more examples that I see from a database, right, in computer science literature or population and statistics literature, the closer my average will be to the overall average, right? That's a so-called weak or strong law of large numbers. So it's a statement that can be proved where we can say close is defined in a well-defined sense, and we can say just how close, right? On the other hand, we can say my average will vary from the overall average, right? It's getting close. How far is it? Well, it'll vary in a way that is described by a bell-shaped curve like the ones I was showing you, with the width decreasing as I see more examples, right? That's called the central limit theorem, right? And the notion of describing the variability or calibrating it probabilistically of a data mean around a population mean, right? That is a thing, right? Central limit theorems, there are entire books on central limit theorems, even though you may see 1, 2, or 3, perhaps, depending on how far you go in statistics in your classes, right? There are dozens and dozens and dozens of central limit theorems where most of it has to do under what conditions can I expect this behavior, right? And it's those conditions that I bring with me as a practicing statistician when I sit down with the problem in astronomy, where the data aren't IID, for example, they're spatial, right? Or in earth science, where maybe the data are sitting on a globe instead of on a plane, right? And these are the things that I bring with me with the expectation that somehow if I have enough data, they look Gaussian-ish, right? Bell-shape-ish. And that's what guides me when I start talking to people about whether we could use, can I use a t-test, which is it's a start of consulting problems more than I can possibly count, right? Is my t-test okay? And we back up and we talk about what is your data and what is your question and how did you get your data, right? And we gradually start moving forward, and I start sometimes explaining to a client things like the statements here. I say, in principle, we expect, but here are some things that we need to happen to let us expect. And all of it is translating the theory to principles, which ultimately is meant to end up with an answer of, let's go with this t-test, or I think you should do the t-test, but also look at a bootstrap, for example, right? And then we have work as well trying to talk about that, when shouldn't we rely on these theory, right? So the chance of being even farther from the overall average becomes exponentially smaller, right? Most things you're going to see are going to keep you near the true average, but sometimes you won't. But that's a very increasingly small amount, right? And that's so-called large deviations. And we can talk about what is that probability. Because in the era of big data, where you're diving into data many times and you're doing many things, we are actually doing so many things or so many looks at data that even infinitesimally small events are actually not that unlikely anymore. So large deviations becomes an important concept. And then finally, if you suppose, what happens if all I see are exceptions, right? Like droughts, like fires raging through an area, right? Like tidal waves, right? And I begin to just look at those types of things. Do I take their averages? There's not many of them and they're kind of unusual. And the answer is no. They actually are an entire different regime. Instead of behaving like bells, they behave like what are called extreme value distributions. And we won't go into those today, but the point is, again, from a statistician's point of view, from a principles perspective, you triage these things and you put them into bins, and that's how you guide yourself when you're going through a practice problem, rather than trying to identify immediately what the tool is. All right, so I'm going to stop here, right? And I'm just going to say that really, did you know you could, see, now I've used the phrase, right? Did you know you could and should approach, in my opinion, any statistical exercise in this fashion, right? Trying to identify what's the questions, what are the data, and then beginning to talk through the principles that should be guiding you until you arrive at a set of tools and a set of code and a set of output. So how about I stop here with the question of what are you interested in discussing?
Right. So at this point, if you're comfortable with it, I would suggest, in order to sort of mimic the brown bag lunch atmosphere, if you can, turn on your video, and then we can have a discussion for the next half an hour. So as Eric said, please feel free. This is an amazing opportunity you're going to have to present your statistical questions to Eric. He's not going to give you prescriptive answers. He warned me that before, when even I asked to do that as a grad student, of course. But I think he'll be able to, look at the big picture and give you an idea how you can approach the problem big picture. So think about it. You can put your questions in the chat, or you could use the raise hand option to ask questions. I have a question that I already had that I'm working on right now. So I might, want to start with that, to give like everybody else a chance to think about questions, if that's fine with everyone else. So my question is, I work with a lot of human data sets, human behavioral study data sets. And one thing that's different with computational data sets or machine-based data sets is that there's a lot of individual variability that's incorporated with the data set. So the group response essentially removes this individual variability when we look at a population in a group sense. For example, I study individuals with Parkinson's disease. So the group response, then I compare with a set of individuals with older adult controls. So I'm comparing the statistics or group mean responses in a group level, but then there's a residual of heterogeneity in the PD group that I'm trying to sort of understand. How do I get to it? How do I study that portion? So without going into detail, I'm not asking for methods, of course, but Eric, if you can give us some insight as to how we can approach that problem.
Sure. Yeah, I'm gonna work like a politician, right? So I'm gonna answer the question that I want to answer. But I would say that, what you're describing at 10,000 feet, it's a very, very common sort of problem. Of course, there's lots of fields that deal with those sorts of design studies and a great deal of variability. And every time we sit down with them, for the most part, the exercise is trying to talk through potential sources of variability. Right. When you do analysis of variance, right? When R.A. Fisher created the concept of analysis of variance back in roughly the 1930s or so, it was meant originally, if you look in his design of experiments, to simply be a way to tabulate, right? All this stuff with F distributions, chi-squares, all of that came later. Right. So really, it was just meant to be a way to literally separate out sources of variability. Right. And so you can think about that from the numerical point of view in terms of an ANOVA table. But if you think about it conceptually, right, you are already talking through some of your sources of variability. And that's typically what I stress with people when we're having a conversation about how to go about modeling, right? Is that, and ultimately, if you look at the history, while analysis of variance is still heavily used, it used to be very much based on all these rules about creating sums of squares and then looking at ratios of means of squares and whatever. All that's done with models now, right? You may still do the ANOVA output because it's a useful table going back to Fisher, but it's all based on models, and models, particularly mixed model methodology, where you have both fixed effects you're trying to estimate, but also random effects due to the variability of individuals, as you were talking about, or the variability of repeated sampling over time. Those are very powerful frameworks for thinking about sources of variability, right? And then once you have identified what you think are appropriate sources of variability, most of the rest of that stuff has been worked out, right? That is one of the benefits of the two-edged sword of software, right? The other edge being that anybody can stick something out and they will get something out. But really, you want to have gone into the software using thoughtfully, having this conceptual model in mind, right? So I think, what my high-level comment would be, what you were describing is just go further down that path. As you're thinking about what are the sources and whatnot. And then if you're not familiar with the modeling, then looking at mixed modeling a bit and reading it from the perspective of how do they capture variability with these model components, right? And if you understand that, then there's doing inference. Okay, at some point you're going to be doing some kind of inferential procedure. You can open the door up on frequentist methods, Bayesian methods, et cetera. But again, not getting lost in the forest for the trees, right? It's an inference, and there will be a mechanism for it, and there'll be some caveats, and you want to look at the caveats and make sure you understand them, and there will be software that needs to be found. But that I don't want to trivialize all the work of it. There are thousands of researchers and myself and students. Yeah, anytime you do a paper, you're spending a ton of work as a statistical scientist putting in all the details to get that right. But when you want to use it, I think it's really useful to come back and figure out whether big picture, these are the right pieces and the right paradigm to do the work. Does that help?
Yes, definitely. That's one. Thank you so much.
Okay.
All right. So we have another question in the chat. George, if you want to present the question yourself, I think that would be much helpful.
Yes, okay. I sometimes prefer not to talk. I remember the talk about physics. I was in a class about climate change, and the expositor talked about using machine learning for physics, but it broke the law of energy conservation, so it cannot work. It is the same case for statistics and machine learning.
So I wasn't in the lecture, so I'm going to guess what I think happened. What I think probably happened is, there's really a fascinating interface going on right now between statistics and machine learning and physics, which is that we have a tremendous amount we know from physical models and physical theory, whether it's in physics or astrophysics or chemistry or materials or whatnot. And these are also sort of laws at a certain level of granularity, kind of like the central limit theorems are, or the law of large numbers in statistics, right? Some of those laws, when you fit data to them, you would like to force the estimation of whatever parameters or whatever learning is being done there to obey those constraints that are dictated by the physics. And if an arbitrary machine learning model is used where it's unconstrained, it's generic, it's off the shelf, then it typically isn't going to do this. And the physical scientists are finding this all over. Right, at Hariri, we had a year-long program where we had machine learning people working with people at various levels of chemistry and materials, for example. And we had some speakers last year in a distinguished speaker series who were talking about where models meet machine learning. And what we're beginning to see is that there's a real sea change in machine learning, and I include statistical learning as a piece of that, right? That type of modeling where you're including as constraints what you feel you know from the physics, from the chemistry or whatnot. And this isn't necessarily new, it's just sort of continuing to be revised and refined and whatnot. Bayesian modeling, for example, in many situations has been a preferred way of doing modeling, say in certain astrophysics situations, because it's ready-made to incorporate what you feel as knowledge in this form of a prior distribution, which is a probability, so it's calibrated. And then when you add data, it similarly is calibrated through Bayes' rule into an output probability. So I would say that statistics applied to such data needs the same fix, which is essentially you're looking at constrained modeling rather than sort of unconstrained modeling. And we're seeing that, I should say. I mean, we're papers in chemistry, physics, blending of differential equation systems with machine learning, for example, is becoming a whole sub area.
Awesome. So we have another question in the chat. If Afra, if you want to unmute yourself and present the question yourself.
Hi, sorry, I'm in the office. So I was wondering, so we use Ttest often when we're reporting our results in mostly deep learning right now, and its relevant applications papers. So why do you, I often see that like the assumptions are violated that are required for the t-test. And I don't understand why people keep using it while there are like alternatives. So I wanted to ask your opinion on that.
Sure. Let me offer a few opinions. The truth probably lies somewhere amidst all of them. One is because that's the primary thing that's taught in a first-year statistics course. And if what you largely have had is a first-year course, then that's going to be your go-to. So that's certainly part of an answer. Second of all is the issue of robustness. So the assumptions on statistical tests, tools, whatnot, don't always have to hold 100%. Sometimes they do. Sometimes they're very brittle. Sometimes they're not. So the studying of t-tests is something that, and their robustness is something that's been studied in a fair amount of detail. I'm going to put something in the chat there for a favorite next book for anyone who's had largely an intro course. This is called Beyond ANOVA. Right, it's a wonderful book. It was written in the 1980s, so I know it's a long time ago, right? But it was written by Rupert Miller, who was at Stanford. He passed away early, unfortunately, but he ran the. He was an excellent statistician anyway, per se, but he also ran the consulting, and so that book actually has a lot of the sort of perspective that I'm talking today as well. But it was meant to literally capture statements and questions like you're asking about kind of the bulk of things that you see in a first year course. So that's why he called it Beyond ANOVA. It has an entire chapter on what are the assumptions on t-tests and when would we expect them to go awry and whatnot, as well as regressions and a bunch of other things. The last thing I would say is that, the landscape continues to change. So permutation tests, they have traditionally been expensive, but compute power is so cheap now that, we are teaching bootstrapping and permutation principles in intro courses now. Berkeley's Data 8 is a great example where it's a merging of computing and statistics, and they teach a bit of Python early on, enough so that they can essentially have people do experiments numerically to learn the principles of testing, after which they introduce things like t-tests and whatnot. So,
yeah, thank you so much.
Yep.
Awesome. So is there any other questions from the group? Yes, Kim, go ahead.
So, I responded that my goal for today was to try to demystify a little bit of statistics. And I do find it a little bit overwhelming. And I guess, I don't know if I have a specific question, but sort of looking for your perspective as I study voice disorders, speech and voice production. You have a background in math and statistics. So you come at statistics from a very different perspective. For me, it feels like this intuitive understanding of the principles and the theories. I'm doing that with the principles and theories of voice production and voice pathologies. So it sometimes feels overwhelming to think that I also need to do it for these tools. So I'm just wondering what advice you have.
So I suppose the advice depends a bit on sort of how deeply you expect, your future to hold, an interaction with statistics. And I don't mean you particularly, I mean, in general. If one is figuring on having a somewhat light brush with statistics, but when they do, it matters, then, close collaborations is a good thing. If one is expecting this is going to be part of one's future, then figuring out where are the right areas to invest in, is a good idea, because ultimately, if the types of measurements you're doing are of a type, then you're going to probably be of an area of statistics that you largely need to become invested in, rather than this whole length and breadth that we're trying to very quickly and in a compressed way put into a Stat 101 course. The challenge with those courses is like, I don't have training in voice. have a little bit of training in engineering because I did signal image type processing things, but it was only because I took a course on Fourier transforms and related, and the rest was self-taught. So, the ability in the way we have our programs typically sort of take multiple layers of courses to get into an area, it's limited. And then those that teach sort of gateway courses like that, they're faced with, well, do we do only a limited amount and it serves less, or do we try and do more and it serves more, but maybe less well than we like? So I would say, for something like yourself, if you're doing experiments, right, then understanding more the principles behind doing experiments and how those principles lead to certain types of models and then the inferential procedures, that would probably be well vested. Some of the roots in modern statistics, again, going back to Fisher and others, I mean, the turn of the 1900s, it was a transition from from traditionally statistics had been viewed as the collection and reporting of data. This is like going into the 1840s, 50s, 60s. It was literally just collecting and tabling it, right? And then moving into the early 1900s, Fisher, Pearson, all these people, this area of these names that you know about, they were moving towards putting more experiments in, sampling in. Those became really sort of how you got your data, became a driver for the development of these methods. So my suggestion would be that sometimes, even though we've seen something, or even if we haven't, being prepped as to kind of how to look at it. For me, it's like art. I love art, but I don't feel I appreciate anything of what I'm supposed to the extent I'm supposed to. I like to at least have someone there who will tell me, yeah, the artist was trying to do this. This was historically where that person was. She did this series of paintings, but then she transitioned to that series of painting. Just a little bit, so that instead of just looking at the swatches of color, I actually get the picture. And then I can zoom in on the swatches if they tell me, look at the brushstrokes. So I guess what I'm hoping to do today is the same thing. If you're doing experiments and you next pick up a book on experimental design or an online tutorial or something like that, try and approach it from the idea of what's the essence of that they're trying to do here. And don't get pulled into the formulas too quickly. Okay. Nor the software, nor even though knowing that, of course, if you want to use it, you'll have to.
That's helpful. Thank you.
Sure.
Awesome. So we might have time for one more question and a discussion. So if anybody has one final question, please go ahead, put it in the chat or raise your hand and ask it. One thing that I wanted to mention is that when I also wanted this kind of a topic to be discussed at the Did You Know You Could series, I was not seeing the bigger picture. And I was also suggesting to Eric, can you please list a number of different formulas we could use for like variance testing or, to find outliers, something, so that I could use as a cheat sheet at the end of the day. But I think what we got from today's session is much more valuable, so that it sort of like takes us away from like using that shortcut and looking at the forest and not getting distracted by the trees. So I think that was very important for all of us. I think we have some knowledge of statistics. We've each taken, I think, 1 or 2 stats classes at least at this point. So it's not really about how to do the stats, but what stats to apply and how do we get to that whole process. So thank you very much, Eric, for letting us see the big picture. This is something that was missing for us for a long time.
Thank you.
So yeah, if there aren't any more questions, I'd like to actually, wrap up today's session. So one thing to remember, because there was a lot of information that Eric shared in the presentation, you might want to have a look back at it. So the recorded presentations will be available in Harari Institute website, in their YouTube site. So on behalf of the graduate students, fellows, thank you so much for joining us. And I also wanted to remind that the next Did You Know You Could series is happening on February 28th from 1 to 2 p.m. Eastern Standard Time. And the topic is, did you know you could train neural networks to model tasks performed by animals? And it'll be presented by Professor Mark Howard. Oh, there is a question. One more question before we end for Eric. Yes.
A good course. Well, the question would be a good course for what? And at what level and whatnot? Feel free to send me an email and we can engage that way. That's like an advising level type question. And anyone who came to me for advising over 20 years can tell you that I never give an immediate answer. It's always about where are you at? Where are you looking to go to? And what tools are you bringing to bear with it and whatnot. So go ahead and just send me something and we can interact.
Awesome. Thank you so much, everyone, for joining us today. Have a wonderful rest of Monday.
Thank you all. Bye-bye.
Thank you.